tout de suite. Good morning. It's a pleasure to welcome today Adam Pond. He is a gravitational wave theorist and will discuss the modeling of gravitational waves from asymmetric binaries. So Adam did his PhD thesis in gravitational physics at the University of Guelph in Canada under the supervision of Eric Poisson, who has been often a visitor here in IAP. And in 2011, he joined the University of Southampton in the UK, the School of Mathematical Science. And he is a principal Royal Society research fellow there. So Adam's research focuses on modeling compact binaries and the gravitational wave signals using sophisticated, as we shall see, approximation techniques based on black hole perturbation theory in general relativity, the so-called gravitational cell force problem, which applies in the small mass ratio limit between two particles. One is supposed to be a supermassive black hole in the center of a galaxy, and the other one is a stellar-sized black hole around it. A great application of all this work is to model the MRI signal, extreme mass ratio in spiral, which is likely to be one of the bread and butter sources for the future detector LISA in space. And Adam Pond is the world expert, I would say, on second order, on developing gravitational cell force at second order in the small parameter, which is the mass ratio between the two particles, and then compare it with other methods, including full numerical simulations. So it's a pleasure to hear you. We are eager to hear you. Thank you, Adam.
Okay, thanks, Luke, for the kind introduction. And thanks for the invitation to give this talk. The last time I gave a talk at the IAP was, I think, 11 years ago. So it's very nice to be back speaking here again. Modeling is in the title of my talk, but I won't actually get to modeling until pretty deep into the talk. I was asked to give a broad introduction, so there will be a fairly lengthy introduction on the topic. But the subject is asymmetric binaries, which, as Luke said, these are binaries where we have two objects, one of which is much bigger than the other one. Okay, and for the sake of the remote viewers, I will use just the mouse pointer rather than pointing with the stick. So hopefully this is clear to everybody. Just to outline the talk, as I mentioned, there will be a broad introduction to begin, just kind of the current status of gravitational wave astronomy and how asymmetric binaries fit into the big picture. And briefly discuss how people model compact binaries in general, leading into how I model compact binaries, which is using this thing called gravitational cell force theory, which is based on black hole perturbation theory, as Luke mentioned. And as Luke also mentioned, the real highlight of recent work is second order in perturbation theory and what we call post-adiabatic waveform models. Okay, so start with the biggest picture. So why are we all interested in gravitational wave astronomy? Well, traditional electromagnetic astronomy obviously lets us see very spectacular things. We learn a lot about the universe. But lots of things in the universe are basically invisible to electromagnetic instruments. So why are we interested in these things that are basically invisible to electromagnetic instruments? Well, one reason is we always think that GR is describing the motion of celestial objects very well on the scales that we can measure things. But most tests of GR have really been in the weak field until very recently with gravitational wave astronomy. And we get the best view of strong field gravity, highly dynamical gravity, by looking at gravitational waves rather than electromagnetic waves. And these areas of very strong gravity are especially interesting because they contain strongly gravitating objects, black holes primarily. So also neutron stars, but neutron stars we can also see electromagnetically. So it's black holes that would be basically invisible to us without gravitational wave astronomy. Which isn't to say that we can't see anything about black holes with electromagnetic waves. Obviously, we've been thinking there are black holes out there for many years already, based on X-rays and other observations. And I always love to play this movie, which is a time-lapse movie of just stars orbiting Sagittarius A star at the center of our galaxy. So here you can see this star orbiting around. It gets a kick. So it's orbiting around something that we can't see in the middle. Now, something is a massive black hole, Sagittarius A star. And now we get an even closer view of it with the Event Horizon Telescope, although this is not Sagittarius A star, this is M87. But now we have pretty close-up views of black holes using electromagnetic instruments, but they're quite limited in what we can see. We can really only see very nearby massive black holes with this kind of instrument. And although we get some very mild constraints on GR, they're very, very mild because the data here is totally dominated by astrophysical uncertainty rather than uncertainty about our theory of physics. So we don't currently get strong constraints at all on GR or on our fundamental theories from this kind of observation. So right now, the best way of observing black holes and observing very strong regions of gravity is with gravitational wave detectors. So this is a picture you've probably all seen before. This is the first detected gravitational wave in 2015, detected by the two LIGO instruments. And this is just a picture you've probably also all seen of the typical form of a binary like this. We have two objects orbiting around each other, emitting gravitational waves. The orbit shrinks until the two objects merge. That's where we have a peak in the waveform. And then we have just a single object, in this case, a single black hole, just vibrating and settling down to a stationary state. So this was a huge breakthrough. This was the first observation of binary black holes. This was the first direct detection of a gravitational wave. This was a major breakthrough. But nowadays, we actually see these all the time. So you can go on to the GraceDB database, which gives all the public alerts every time there's a detected gravitational wave. And so here I've just highlighted the dates of the most recently detected waves. So one on May 20th, one on May 15th, two on May 14th, one on the 13th, one on the 12th, one on the 11th. Some of these do get basically retracted when they decide, okay, it wasn't strong enough evidence that we actually detected something. But we're detecting primarily black hole mergers all the time now. In the current observing run, LIGO and Virgo have detected just under 100 or just over 100 signals already. And there were already about 100 in the previous observing runs as well. So we now see these things all the time. And we've already learned a lot from these signals. We've learned about the population of black holes in the universe, which is probably much bigger than we had thought 20 years ago. We have some constraints on GR, on our fundamental theory. We have learned a bit more about neutron stars that we couldn't extract before from electromagnetic signals, although the vast majority of these signals do not involve neutron stars, but occasionally we see them. But this is just the first step. So we see these things all the time, but they come in a pretty limited range of what we can see because of the particular frequency spectrum that we can detect with current observatories. That's all going to change over the next 15, 20 years, where we're going to have a lot more detectors come online. So here are the currently running detectors. We have the two LIGO observatories. We have Virgo. Geo16 was basically just a proof of principle, so it's not actually detecting anything, but it's still there. Cagra is currently not operating because of the earthquake, but the hope is certainly that it'll come back online and reach design sensitivity soonish. And LIGO India always has a very, very ambitious schedule. I don't know if anyone in the room knows more about that than I do. They always seem to say it's 5 years from now it will be operating. Basically because it's just using LIGO instruments, so it doesn't take a long time to set up. So we will have a whole network of detectors on Earth. All these detectors I mentioned see basically the same frequency spectrum as each other, but we're also going to have additional detectors that can see a lot more. So in space, there have been these long-term plans for this Japanese detector DeSiGo. I don't think that's really funded and ready to go, but there have been lots of discussions of it. LISA, which will be more of my interest here, LISA is funded. It was just formally adopted as a European Space Agency mission in January. So it's now actually rolling. It's ready to go with an expected launch date of 2035. And that will see totally different types of systems than what we can currently see. There are also two different space missions being put forward by China. Probably just one of those will be selected, but currently they're in competition with each other. And then we have much more sensitive, much bigger ground-based detectors as well, what are called third-generation ground-based detectors, the Einstein telescope in Europe and Cosmic Explorer in the US. So all of these things will allow us to see a lot more kinds of systems, a lot more systems in general, and systems much further away. Now here's a plot of the sensitivity curves of most of these detectors. So basically, if a signal is above the sensitivity curve, so here's one sensitivity curve in black, all the sensitivity curves are in black. This is a function of the waveform frequency. If a signal is above that threshold, then we can detect it. And so the current detectors that we have, this is advanced LIGO here, are around 100 hertz. Einstein telescope is this one down here, so it's seeing basically the same spectrum, but with much better sensitivity, so the whole threshold is moved way down. LISA is at much lower frequencies in the millihertz regime. And DeSiGo, if it ever is launched, is in the middle. And then way down here, you have pulsar timing arrays at very, very, very low frequencies. And this range of frequencies is very important because roughly the frequency of the wave is inversely proportional to the mass of the system generating it. And so the lower the frequency, the bigger the system, the heavier the system. So what the pulsar timing arrays see is a background from supermassive black holes, a billion solar mass black holes, a very, very low frequency. What we currently detect with ground-based detectors is basically stellar mass black holes, 1 solar mass up to 100 solar masses. And then LISA will see things in the middle in the massive black hole range, in addition to other things, but massive black holes in particular, which are 10 to the 5, 10 to the 6, 10 to the 7 solar masses. So with this range of frequencies that we'll be able to observe, we'll be able to observe lots of different kinds of binaries. So the simplest kind of binary, which is the one that we currently detect all the time, is called comparable mass binary. So this is where the two masses are comparable to each other. Neither one is much bigger than the other one. This is primarily what we see with the current network of detectors, LIGO, Virgo, Cagra. And we see them in the stellar mass regime, where both of the objects are 1 solar mass up to 100. LISA will see these same kinds of systems, but just much, much heavier versions of them, where we have two massive black holes. So if we have two galaxies colliding, each one of them will have a massive black hole at its center, and then those two massive black holes will form a binary. And we will see comparable mass binaries that are a million times heavier than what we currently see. And those will be basically the loudest signals in the universe, with SNRs in the thousands. Then we have intermediate mass ratio inspirals. or IMRIs, where the mass ratio, the small mass to the big mass, is 1 to 100 or 1 to 1,000 in that range. These are largely interesting because they contain intermediate mass black holes, and we still know very, very little about the population of intermediate mass black holes, or if there's actually just a gap where no masses exist, where there are no black holes. So if we see a bunch of these, well, then we learn a lot about the existence of intermediate mass black holes. We've already observed black holes with masses, 130 solar masses was the heaviest. So we know that they do exist, but there might still be a gap between, a few hundred and a few 100,000 or a few tens of thousands. And that will be important to observe these because then we'll learn about the whole history and evolution of black holes over the history of the universe. And possibly where massive black holes originated. Maybe they originated from intermediate mass black holes. Then the kinds of systems that have really motivated the method I'll talk about, the self-force method, are called extreme mass ratio in spirals, or EMRIs. So here you have a mass ratio 10 to the minus 4 down to 10 to the minus 6 or 10 to the minus 7. So the big mass is tens of thousands up to millions of times bigger than the small mass. So as Luca mentioned, these will be key sources for LISA. Really, the two biggest targets for LISA are the massive black hole mergers I mentioned and these, EMRIs. So these occur in galactic cores when a stellar mass object is captured by a massive black hole. So here, the massive black holes, mass of 1 million solar masses, and then we'll have just a stellar mass object orbiting around it. The stellar mass object is most likely going to be another black hole, but it could be a neutron star. Or it could even be a white dwarf that then gets tidally disrupted right at the end, and then in principle, you could have an electromagnetic counterpart, but that's somewhat less likely. We expect these to be mostly black holes. And these systems are very, very interesting because they're very, very tightly bound systems where the smaller object is really probing the very strong field regime right around the massive black hole. So here, I'm just getting a shot from that video I showed you earlier, where we had the star orbiting around Sagittarius A star. Now, the closest known star around Sagittarius A star is about 200 Schwarzschild radii at closest approach. EMRIs, we expect to spend hundreds of thousands of orbits within 10 Schwarzschild radii of the massive black hole. So this is a much, much, much more compact scale than what we observe stars going around the center of the galaxy. The number of systems we see like this is very uncertain. Estimates range from a few up to a few thousand in the lifetime of LISA, with the kind of the peak distribution is most plausible will be maybe 100 of these will be observed over the lifetime of LISA. Now, what can we learn from systems like these? Well, one thing is about what is a black hole. Is a black hole what we think it is? So in GR, all black holes that are approximately stationary and approximately isolated, they all have a unique form. They're all the same as each other. They are all described by the Kerr geometry. So every approximately isolated, approximately stationary black hole in the universe, we think, is a Kerr black hole that's specified just by its mass and spin. But that is an outcome of GR. That's a prediction of GR. We don't actually know if the dark objects that we see really are Kerr black holes. Something like the Event Horizon Telescope actually puts really, really weak constraints on whether it is a Kerr black hole. Can't even really measure the spin, let alone anything else. So we have tons of evidence of what we think are black holes, but the really precise evidence that they are the black holes we expect is almost totally lacking. It could be something else entirely. Now, because MREs, you have this small object executing all these super tight orbits around the massive black hole, that acts as a probe of the geometry around the black hole. And we'll actually be able to say very, very precisely, is this a Kerr black hole or something else? Way more precisely than any other planned experiment. And every week you'll see a new paper on MREs, on what we can learn from MREs. So what I just mentioned is basically this first one, where we measure the central black hole parameters. We can measure, or we expect to be able to measure the mass and spin of the black hole to within about 0.01% error. And then to test whether it is a Kerr black hole or something else, we can also measure the quadrupole moment. So if it's a Kerr black hole, every single multipole moment is uniquely determined by the mass and spin. So if we're able to measure the mass and the spin and the quadrupole moment, then we can check, does it satisfy the relationship that it should if it's a Kerr black hole? And we expect to be able to measure the quadrupole moment to about 0.1%. So then we can very precisely say, with orders of magnitude better precision than any other experiment, is this really a Kerr black hole or something else? But we also expect to learn a lot of other things from observations of MREs. So they'll be very sensitive to new fundamental fields. If there's a new scalar field, a beyond standard model scalar field, or some other fundamental modification of GR, these systems are very sensitive to that. And we expect, or hope to be able to get very precise measurements of presence of new fields beyond standard model, or presence of deviations from GR. We also expect to get a lot of astrophysical information from observations of MREs. So for example, massive black holes are surrounded by dark matter halos, and there might be a cusp, a high density cusp around the black hole. If there is, then the MREs will be sensitive to that, and we'll be able to infer properties of dark matter. We can also measure other properties of galactic cores. So for example, we can measure properties of the accretion disk. And there will always be other bodies orbiting somewhere around. And if they're close enough, we can also measure the presence of them. So we get some sense of what is the stellar distribution around massive black holes and galactic cores. Also, just by measuring all of these masses very precisely, we'll be able to constrain the mass function very well. So the number of black holes in the universe with a given mass. There are many other things I'm leaving off this list. We can also do some cosmological measurements. If we measure multiple MREs, we can use them as standard sirens, and we can measure the Hubble constant probably to around 1%. So by the time we get that measurement, that might not be competitive with the best alternative measurements, but it's totally an independent measurement of the Hubble constant. Okay, so that's my big picture introduction. I'm now going to talk about modeling these things. So gravitational wave astronomy is a bit special in the sense that the data we collect tells us absolutely nothing unless we have a good model telling us, first off, how to find a signal in the data. Sometimes, actually a lot of the time, you can't see that there's a signal until you know what you're looking for. But especially you need a very precise model of what the waveforms should look like in order to be able to extract information about the systems that created them. So we need something that says, okay, if you see a signal that looks exactly like this, that means it's coming from a system that looked exactly like this. Now, for the kinds of systems that are currently observed by ground-based detectors, there's a very nice kind of paradigm of how we build the models. So this is a picture from Luke. The signals look like this, like sinusoids that get a higher and higher frequency and amplitude ramping up. In the early in-spiral, we can use post-Newtonian theory, weak field, slow velocity approximation. Right around merger, the only really precise thing we currently have is numerical relativity. So that's exactly solving the fully nonlinear Einstein equations with supercomputers. And then at the end, well, we still have numerical relativity working there, but you can also use black hole perturbation theory. So there you just have a single black hole that's vibrating, and so that's well described by just perturbations on top of a Kerr black hole. And it just rings down into a steady state Kerr solution. So that's the current paradigm, but that's really focused on the kinds of systems we currently observe, which are quasi-circular, comparable mass binaries. In particular, comparable mass, but also most of the focus has been on quasi-circular as well. Now, even with current ground-based detectors, we are already seeing systems that are not really comparable mass. We've seen a system with mass ratio 1 to 25, which as far as numerical relativity is concerned is pretty extreme. Numerical relativity is really focused on almost equal mass systems. So even for current detectors, we need to kind of improve our coverage of parameter space. But certainly for future detectors, where we expect this huge range of mass ratios, we need to really have a whole separate way of modeling them. So here's a picture of the two most important axes in the binary parameter space, the separation between the two bodies, and the mass ratio. This is the big mass ratio, so large mass over small mass. So it's going from 1 to infinity. And so as I mentioned, post-Newtonian theory is up here in the weak field, large separation limit. Numerical relativity is down here in the corner. And, of course, in principle, numerical relativity can cover everything. It's just a matter of how long can you run your simulation for. So in reasonable runtimes, meaning runtimes in scale of months for just a single waveform, you're restricted to pretty small separations and to comparable masses. You really cannot go to very extreme mass ratios. So a typical binary we currently observe would start somewhere over here and then evolve down here and then merger. What I'm going to be talking about is this corner down here. So this is when you have a large mass ratio or small, depending on which ratio you're looking at, where one object is much bigger than the other one. And so this is using a particular kind of perturbation theory where you're saying, okay, my zeroth order solution is just this big black hole, and then I'm just adding corrections on top of that coming from the presence of the smaller body. And we call this self-force theory for reasons I'll explain now. Okay, so what is self-force theory? Why do we call it that? So to motivate it, I'll go back to introductory GR, the equivalence principle. So the equivalence principle says that a freely falling observer measures the same thing that an observer moving at constant velocity in flat space-time would see. So let's go back. Nope. There we go. Okay, so here we've got a picture of something orbiting around a black hole and an observer falling in. And in a local patch, everything looks basically locally flat. And in flat space-time, everything moves, freely falling things move on straight lines. So the generalization, of course, to curved space-time is that everything moves on geodesics of the space-time geometry, which are as straight as we can make a curve in a curved geometry. Now, that is just an approximation. That's a limiting statement. That's a statement that if you have a sufficiently small region and sufficiently light objects that are not creating a lot of gravity, then in the limit of completely being able to neglect their gravity and completely being able to neglect their size, they move on geodesics. So that's an approximate statement. That's not an exact statement. So in reality, if we put a gravitating object in this space-time, so here, this is the space-time of a black hole where it just keeps getting more and more curved. If we just drop an object into it, the object deforms the geometry because it's gravitating. And so this little tiny deformation of the geometry reacts back onto the small object, affecting its motion and exerting what we call a self-force. So this is a correction to the equivalence principle. This is the first subleading term beyond geodesic motion. And every object in the universe, of course, feels a self-force because everything gravitates. There's no such thing as a true test mass. Everything gravitates. In most circumstances, it's incredibly tiny. So I did this calculation a few years ago, so I might be misremembering, but if you put an astronaut orbiting around Earth, the self-force exerted on the astronaut by its own mass is roughly 1/trillionth of 1/trillionth of the astronaut's weight. So obviously not something we can measure. Now, in an emery, you have a very compact object, a little black hole or neutron star. There, the self-force is much more significant. But even so, its instantaneous effect, its effect at one instant in time, is really, really tiny. But it accumulates over time. It has a big long-term impact, which is what actually drives the inspiral of the little mass into the big mass. It's the long-term impact of the self-force. So if we want to model emeries well enough to extract precise information from a signal, we need to model this self-force with incredible precision. And we need to model it for potentially hundreds of thousands of very intricate orbits. And I'll show you just how intricate in a second. So that's kind of the big conceptual picture, but mathematically, what are we actually doing? So mathematically, we're saying, let's take the space-time geometry, the space-time metric, and split it into a background piece, which this is a totally general framework, so this could be any space-time, but for modeling emeries, the background is going to be the metric of the large black hole if it were isolated, as if it were isolated, not interacting with anything. So this would be the Kerr geometry unless you have some big deviation from GR. Then we have these little corrections, where here epsilon is the small mass ratio, little mass over big mass. So we have first order corrections, second order corrections, etc. And there's a reason why I'm specifically truncating at second order that I'll get back to later. And so it's these little perturbations to the geometry that then affect the motion of the gravitating object and exert the self-force. So if we write down the covariant acceleration, meaning the covariant acceleration in the background geometry, if it were a test mass, the right-hand side would be 0. If it's a gravitating mass, then we get these corrections, which we call first order self-force and second order self-force. So F1 comes from H1, F2 mostly comes from H2. Now, the equivalence principle, as I mentioned, isn't just saying that the object is sufficiently light that we can neglect its gravity. It's also saying it's sufficiently small. So on the right-hand side here, in addition to self-forces due to gravity, we also will have finite size effects. So forces coming from the spin of the small object, forces coming from the quadrupole moment of the small object, etc. And the way we derive this equation actually serves as a proof of the geodesic principle, that at 0th order, you get geodesic motion. Now, I will not go into the derivation at all, because I want to get into the actual modeling. So to understand how we model these systems, we can start with just 0th order, which, as I said, is just a test mass on a geodesic of a Kerr metric. So you can see from this picture that this motion is already very, very complicated. This is not what you're used to in Keplerian dynamics, where you just get, little ellipse, or even what you're used to from looking at orbits around a Schwarzschild black hole, where you might whirl around and go back out, and whirl around, go back out. It doesn't look like this. So this is a feature of the spin of the large black hole that causes this very complicated motion. But even though it's so complicated, it is still integrable. We have enough constants of motion to make the system integrable. So the 3 constants of motion are the orbital energy of the orbiting particle, the azimuthal angular momentum. So here, if the spin axis is pointing directly up for this black hole, this is the angular momentum, the orbital angular momentum of the orbiting body around that spin axis. And then we have something called the Carter constant, which is directly related to the orbital inclination. Now you see here, the orbital inclination is not constant. This thing is oscillating up and down. But the Carter constant is related to basically the maximum inclination. Now, basically, because it's integrable, the way it works out is that these orbits are tri-periodic. So they have three distinct, generically incommensurate frequencies: a radial frequency, a polar frequency, and an azimuthal frequency. So the thing is orbiting around and around like this, and has an associated azimuthal frequency. It's coming in and out due to eccentricity, and there's a frequency associated with that. And the whole plane is going like this, and there's a frequency associated with that. And generically, these three frequencies are not in rational ratios to each other. They're independent of each other. So associated with each of these frequencies, we can define a phase. We have three phases of motion that run over 0 to 2 pi in one radial oscillation, or 0 to 2 pi in one polar oscillation, or 0 to 2 pi in one azimuthal orbit. So these are basically action angle variables. So we can define these phases such that they have a constant rate of change that's exactly equal to the frequency. So three frequencies, three phases. And then we're describing the whole dynamics by 6 equations. 3 of them are just the rate of change of these 3 is 0. And then 3 of them are these, that the rate of change of the phases is just equal to the frequency. Now that's just the 0th order test mass motion. Once we turn on the self force and we allow the object to gravitate, then the self force causes E, L, and Q to slowly evolve. These are no longer constants of motion. They're evolving gradually over the course of the inspiral. But we have a very clear separation of scales. We have 2 distinct time scales in the system. We have the orbital time, which is the time which is for one of these revolutions, or polar oscillations, or radial oscillations. So we have an orbital time associated with that. And then we have what's called a radiation reaction time, which is the time it takes for these E, L, and Q to change by a significant amount, by an order 1 amount. And the radiation reaction time is 1 over the small mass ratio. So if you have a mass ratio of 10 to the minus 5, then the radiation reaction time is 100,000 times longer, approximately, than the orbital time. And on the radiation reaction time, Hinder and Flanagan showed quite a few years ago now that those 3 orbital phases we talked about have a very clean, nice-looking asymptotic expansion. It looks like this. So this is on the long time scale, meaning the argument here is epsilon times t, so that t needs to change by order 1 over epsilon for the argument to change by order 1. And so on this long time scale, the phases have an expansion like this. They start at order 1 over epsilon. That's because they're roughly growing secularly or linearly in time. So if you have a time of order 1 over epsilon, you also accumulate a phase of order 1 over epsilon. Then you have a subleading correction, epsilon to 0, order epsilon, and so on. And based on this scaling, we can say, okay, the main thing we need to track when modeling a waveform is these phases. That's what we need to get very, very accurately. And we can say, based on this expansion, that for sufficiently small epsilon, so for sufficiently extreme mass ratios, this term is negligible. And therefore, we just need these first 2 terms. Now, we probably cannot neglect this term. Almost, well, now we have evidence you cannot neglect this term, because an order 1 impact in the phase is very bad if you're neglecting it. So the goal for the last 20 years has been really to get an accurate enough model to calculate these 2 terms. This first term gets called adiabatic order. It's determined by, well, geodesic dynamics, but also by the averaged dissipative piece of the first order self force. So you need to calculate part of that first order metric perturbation, H1, to calculate part of F1, to calculate the phase at this leading order. Then the next term is called first post-adiabatic order. So these are usually denoted 0 PA for adiabatic and 1 PA for first post-adiabatic. This term, well, you need the rest of the first order self-force, meaning you need all of H1, all of the first order metric perturbation. And you need an averaged dissipative piece of the second order self-force, which again means you need part of the second order metric perturbation. So historically, over the past 100-odd years, when people are doing black hole perturbation theory, almost exclusively, they're doing linear perturbation theory. You're adding just a linear perturbation on top of a black hole background. But to do this correctly, we need the next term. We need to go to second order in perturbation theory. Now, the way we do this is based on multi-scale expansions. So we need something that really maintains accuracy over all these orbits, these hundreds of thousands of orbits, and can generate waveforms very, very quickly. Because we have two requirements for gravitational wave data analysis. One is accuracy. We need a good model. But one is speed. We need to be able to generate waveforms very, very rapidly. And so the method we use that covers both of those bases, accuracy and speed, is this multi-scale expansion of the Einstein equations. So remember, for a geodesic, what I had was that the rate of change of the phase is just the frequency, and then the rate of change of these three constants of motion was just 0. If you choose very nice coordinates on your perturbed phase space describing the orbit, you can put the full evolution equations in this form. This includes all the effects of the first and second order self-force. The first equation still looks just like the geodesic one, but now we have non-zero rates of change of EL and Q. These are some deformed versions of EL and Q, and some deformed versions of the phases. And the rate of change is specifically order epsilon. So we have an order epsilon term. That's the 0 PA term coming from H1, and epsilon squared term, that's the 1 PA term coming from H2, roughly. So if we choose very nice coordinates to describe the orbit, we have very nice evolution equations. And in particular, there's no oscillations on the right-hand side. We only have slow changes on the right-hand side, which allows us ultimately to solve these ODEs very, very rapidly, because you can take really big time steps because things take a long time to change. Now we have a coupled problem here. We have orbital dynamics and we have the Einstein equations. The Einstein equations are really what's determining what the waveform is and what the self-force is. Everything comes from the Einstein equations. So we need to solve the Einstein equations, but we do that in a way that takes advantage of these really nice coordinates for the orbit. So rather than trying to just directly solve the Einstein equations on space-time, where you have a metric that's a function of time and some spatial coordinates, instead we promote the metric to live on the orbital phase space. What that means is these metric perturbations, rather than being functions, explicit functions of some coordinate time, they are now functions on the phase space. They depend on the orbital parameters, the orbital variables, rather than directly on t. So of course, in reality, in the space-time, they do depend on t, but only through the time dependence of these orbital parameters, these orbital variables. So then you substitute that ansatz into the Einstein equations, you formulate things order by order in epsilon. We do a Fourier series in the phases, so we have amplitudes times kind of rapidly oscillating phase factors. And then what we do is, once we've extracted out the phase dependence with a Fourier series, then we have amplitudes that are just functions of these slowly evolving parameters, the EL and Q. And we can then solve these Einstein equations on a grid of orbital parameter values. So we pick an E, we pick an L, we pick a Q, and we also have to pick a spin of the big black hole. We then solve the Einstein equations to get these H's, but specifically Fourier coefficients that appear in the H's, and to get these forcing functions, these capital F's that appear in the evolution equations for the orbit. So we do a big pre-computation that's very, very expensive. The plots I'm going to show you later really required, I don't know, probably in the millions of CPU hours. But this is all done in advance. You do all this solving of the Einstein equations in advance. Then you've got your waveform amplitudes just stored at infinity. You've got your forcing functions here in these ODEs just stored. And so then you just solve these ODEs and out pops your waveform. So you generate the waveform as soon as you solve the ODEs. And you can do that very, very quickly in a tiny fraction of a second. So right now it's depends on the complexity of the orbit, but tens of milliseconds up to hundreds of milliseconds, which probably is still actually not good enough for data analysis. We might need to speed that up even more. But when you compare that to generating a single waveform in numerical relativity that takes a week, if you're lucky, it's very, very fast. But it requires this very slow, expensive procedure of first solving Einstein equations on this grid of parameter values. Okay, so just to give you a sense of what the waveforms look like, here's a pretty complicated orbit. The waveform I'm showing here is not an exact waveform. It's not even a 1 PA waveform. It's a quite good approximation to a 0 PA waveform. And this is the kind of orbit that generates a signal like that. Very, very, very complicated. In general, it looks like a mess. Occasionally, it passes through resonances that you could have seen just for a moment there, where things look nice, geometrically pretty. The whole orbit shrinks, shrinks, shrinks. In the video, it looks like the black hole is getting bigger and bigger. That is just the camera zooming in. The black hole is almost constant in size, and it's really just the orbit shrinking. So that produces a very complicated waveform like this. They can get even more complicated. This is for pretty mild eccentricity. But that, as I said, is 0 PA. What I really want to focus on now is the latest results at second order, or 1 PA. So solving the second order Einstein equations to generate post-adiabatic waveforms. And that's really what I've been focusing on for the past 15 odd years. So this is a picture of the first 1 PA waveform that was ever produced. This is for quasi-circular non-spinning binary. And we do not expect emeries to look like that. So this is not realistic. So there's a lot more work to do. But it's working very well. So I mentioned that generically we've got 3 phases and three constants of motion, or 3 slowly evolving variables. For quasi-circular non-spinning binary, we just have 2 phase space variables. We have just the azimuthal angle of the orbit. And as one of our variables, we can just pick the azimuthal frequency itself. We don't need to go through energy or angular momentum. We just pick the frequency. And so we do exactly what I described. We solve the Einstein equations on a grid of omega values. We store everything we need, and then we can generate waveforms effectively instantly. So these waveforms in particular are like sub 10 millisecond waveforms after a few million CPU hours to generate the input data. Now, what I'm showing you is for mass ratio 1 to 10. For really extreme mass ratios, we have nothing to compare against. We can compare against post-Newtonian theory in the weak field limit. And Luke and David and I are working hard on doing that comparison, and it looks great. I won't show those results because they're a little bit technical, but that's only the weak field limit. So to probe the strong field limit, the best thing we have to compare against is exact numerical relativity, or roughly exact numerical relativity. So this is mass ratio 1 to 10, which is not the intended regime of use of self-force, but there are 2 waveforms here that agree extremely well. So this is our 1 PA waveform in orange. Here we've aligned the frequency and phase basically at the earliest time that we can back here. And then we just let it evolve and track the dephasing. And we maintain phase coherence very, very well up until right near the merger. Right at the end here, I think this is 0.3 radians of error, or on that order of magnitude. But then the important thing is we know the error in the phase scales linearly with epsilon. So if we have 0.2 radians of error for mass ratio 1 to 10, then if it's mass ratio 1 to a million, it's 100,000 times smaller. So way, way, way smaller than what we actually need. So we have pretty remarkable accuracy, even mass ratio 1 to 10. I think I'm not showing plots for mass ratio 1 to 1. As you can imagine, it's not perfect for 1 to 1, but it's way better than you might naively expect. Now we have gone a bit beyond that by adding some more complexity to the system. So these are quasi-circular inspirals with spin. Now, we haven't done the full problem of solving the first and second order Einstein equations on a Kerr background for a rapidly spinning black hole. But what we can do is add just linear in spin terms, linear in the big black hole's spin terms. And we can add the secondary spin quite easily, the spin for the secondary small object. We can add that quite easily. So now we have a slightly bigger phase space. We have the azimuthal angle of the orbit. And now we have a spin precession phase. So as you can see in this picture, if the spin is not aligned with the orbital angular momentum, it precesses around. So we have a phase associated with that. And so we also have a parallel component of the spin and a perpendicular component. So what I'm showing you here is mass ratio 1 to 4. So Q here means the big mass ratio, big mass over small mass. This is mass ratio 1 to 4. For non-spinning primary, but for a secondary that has quite large spin, and it's not aligned with orbital angular momentum. And here, even for mass ratio 1 to 4, things agree quite well up until pretty late. For comparison, the blue curve is where we just turn off, we ignore the secondary spin. And there you see we totally dephase from numerical relativity. So we see that the spin terms we are adding are doing what they should be doing, bringing us into phase with the full numerical relativity. Here's a case where we have a spinning primary with spin of 0.08. So for black holes, the spin can go from -1 to +1. So this is slowly spinning, but not totally negligible. And we have a rapidly spinning secondary. This is mass ratio 1 to 8. And you see we maintain phase coherence until pretty much right at the end. Okay, but all these waveforms I'm showing you, they just stop before we get to the merger. And that's because this multi-scale expansion I mentioned, the assumption in that expansion is that the rates of change of these orbital parameters is order epsilon. And right at the end of the inspiral, that assumption is just wrong. So as you reach the innermost stable circular orbit, the rate of change goes way up, and it scales not with epsilon, but with epsilon to the 2/5. So if epsilon is very small, that's a much more rapid rate of change than during the slow inspiral. But we can still use the multi-scale expansion. We just need to account for the fact that the rate of change is different than what we had assumed before. So this is ignoring spin. This is quasi-circular non-spinning. And we just use scaled phase space variables. So we have the azimuthal orbital phase. And then rather than using the frequency, we use a scaled frequency that's the innermost stable circular orbit frequency. It's the frequency minus innermost stable circular orbit frequency. So it's kind of the distance in frequency space from this innermost stable circular orbit, and then divided by this epsilon to the 2/5, so that our variable is order 1. Because as I said, the rate of change is epsilon to the 2/5. So here what I'm showing you, okay, the place where these are aligned is way off to the other side. Your perspective way off to that other side. Just zooming in on the last few orbits here. And so the orange curve is our in-spiral 1 PA approximation. And then we can switch to a transition to plunge approximation, which is using these scaled phase space variables. And you see that gets us through the ISCO. Everything looks very good and gets us almost to the merger. Now, the transition to plunge approximation also breaks down, because once you're past that, then you're in an actual plunge regime where the secondary only completes about 1.5 orbits before the merger. And in that regime, the rate of change of the frequency is just order 1. There's no suppression by any power of the mass ratio. So to get the full waveform, we need to add a third regime to cover the merger and the final ring down. Okay, but this is the current state of the art. About 10 minutes behind schedule. So just the things to take away from this. So as I introduced at the beginning, these asymmetric binaries, IMRIs and EMRIs, will be kind of key targets of next generation gravitational wave astronomy. Detecting them and extracting information from them will give us a lot of unique tests of GR, of our theory of black holes, fundamental physics, a lot of information about the astrophysics in galactic cores. The way we model them is using self-force theory, and in particular, multi-scale expansions of self-force theory, which are both fast and accurate. Now, I didn't really cover what is the current state of the art other than those waveforms I just showed you, which are the most accurate thing we've got, but for a quite narrow range of parameters. In principle, we now have leading order 0 PA waveforms for generic orbits and Kerr. In principle, not in practice. And I'll just leave this here for you to read. Okay, thank you for your time.
Thank you very much, Adam, for the nice talk. And so we shall now take questions for you.
Thank you for the talk. Do we know how big the spin of supermassive black holes is? For example, Sagittarius A star or the one in M87?
There are estimates that range a lot. Most astronomical data suggests quite high spins for massive black holes, like 0.9 or above even. Depends how you define it, whether you count for its direction. But yeah, between 0 and 1 magnitude, yeah. Assuming it's a Kerr black hole. Yeah.
Precisely about that. You mentioned the possibility to determine if it is a Kerr black hole or if it is something else,
yep.
i.e. something else than GR. Are there any degeneracy which you have to play with for that, or is it going to be obvious?
This is the big critical question. So as I said, every week someone will put out a paper saying, we can measure this with EMRIs, but they never account for the fact that 100 other people have said we can measure other things. And the critical question is, will we be able to distinguish all these things, or are they degenerate? So the hope that we can distinguish between fundamental physics effects, astrophysics effects, is based partly on the fact that the systems are very complicated, so that they're sensitive in different ways to different effects. But really, it's that if we measure a whole bunch of these, we expect the astrophysics to vary a little bit from place to place, whereas the fundamental physics should not. But this is the big question for data analysis right now, degeneracies.
Thank you for the very nice talk. Back in grad school, there was a exercise that we used to do, which is the Kerr-Neumann black holes. I don't know if this was purely academic or there's actually hope to detect charged black holes at some point.
It's academic.
It's only academic.
Yeah, so we expect black holes to always be neutralized just because there's other stuff around that will opposite charge and will neutralize the charge. People do talk about the potential of spontaneously scalarized black holes, which will have a scalar charge. That's an alternative theories of gravity.
Okay, next.
Thank you for the interesting talk. Regarding the previous question, because you are, you are using the orbital parameters for the solution of Einstein equation. Two problems arise. How much degeneracy you see with respect to the, for instance, you at the end you mentioned circular orbits, but in general, it is expected that two sources probably initially are not in a circular orbit. How much degeneracy you see because of this? And my second question is how much you can control numerical errors such that the solution stay. I mean, you don't get too much far from a covariant. I mean, the covariance of the whole process.
So numerical errors we can control extremely well. So at 0 PA, the leading order approximation, we can calculate things with 10 to the minus 15 error very easily. Well, okay, we can calculate the inputs I talked about, those forcing functions with 10 to the minus 12, 10 to the minus 15 relative error. Then it becomes an interpolation problem. You need to interpolate over all this data. And that is what people are still working on, doing that very accurately. That should not be ultimately a limitation. So right now, the big problem for us is covering the parameter space rather than error. Errors we can make pretty small. It's just getting coverage of the whole parameter space. So the reason I went back here is to show an eccentric inclined waveform, which looks, visually totally different than the quasi-circular. So there's no degeneracy between those kinds of things, between the orbital parameters. We can very easily detect a deviation from circularity, but there's still a little bit of degeneracy between things. A little bit, yeah. We can definitely easily see eccentricity, easily see orbital inclination. Once you have the full complexity, you can get like peaks in the likelihood that are not the genuine peak, like neighboring subdominant peaks. So that's also a problem. But the bigger problem is once you start adding other effects beyond vacuum GR, then those effects can be degenerate with GR effects, and then it becomes very, very difficult.
Next question.
Yeah, thanks for the very nice talk. I had a naive question. The post-Newtonian waveforms do have the exact mass ratio information, right? So does it mean that these can be replaced by post-Newtonian waveforms in mildly relativistic systems, or?
Oh, and mildly relativistic, yeah, definitely. The post-Newtonian will be better than this.
Okay.
Yeah.
And hence we need comparisons with both post-Newtonian as well as numerical relativity to get a.
Yes, we have done extensive comparisons with post-Newtonian. It's just I didn't have plots that were as easy to look at as this.
Okay. And
so our first check is always against PN.
So just a quick follow-up. Even post-Newtonian waveforms will be working at last stable orbits?
No.
No. Okay.
Well, not so bad.
For Q equals
yes.
1, not so bad.
Yes.
For Q equals 10, very bad.
Yes.
Okay, so what sort of frequencies where we should assume that, this will...
So it's really a function of mass ratio. So the smaller the mass ratio, the smaller the range of frequencies that PN is good for. And it's the same with self-force. The weaker the field, the more self-force terms you need to get accuracy.
Okay, thank you.
So we understand that for this talk, you had to skip many important and difficult details. So I'd like to ask a technical question about these details. Mm-hmm. And there is an important one, which is related to the regularizations that you have a particle, so you have to somehow remove the self field of that particle in order to describe the motion and radiation. Mm-hmm. And it happens that you have several schemes to define the regularization in the self force that are equivalent. And on the other hand, when one compares to other approximation, for instance, post-Newtonian, we have different types of regularization as well. For post-Newtonian, this is dimensional regulation. And it happens that the results are consistent to each other and it works extremely well. So do you have a comment of why all these regularizations give actually the same result?
So if you have the correct waveform, it doesn't care about what regularization you did on the way. So the waveform itself, either you have the right answer or you don't. So you would expect them to be consistent. What's more interesting is when you calculate specifically the redshift, the Detweiler redshift. So that's something you can define that's from a regular piece of the metric perturbation. And that agrees very well between Pn and self-force, at least at first order. And that you could think, well, this is just something artificial I've constructed. Why should they agree? And there's some indication in that last paper that you sent me the email about. So there we found that the regularization that's used at first order in self-force, so I should say at second order, there's only one regularization scheme that has ever been looked at or used. It's based on matched asymptotic expansions. So there we say we have the approximation I talked about for the whole talk in most of the space-time. And then in a little region of order epsilon size around the small object, we have a totally different approximation that kind of zooms in on the small object. And everything we do is basically saying we enforce consistency with that limit. And so in that sense, there isn't any real regularization. We have something finite outside a small object, and we just insist that if we're close enough, it has to look right. At first order, that gives you the same answer as when you just take a point particle and do what's called the Detweiler-Whiting prescription to regularize the field. And in the paper I put out whenever that was, a couple months ago, there I realized that the Detweiler-Whiting prescription actually gives you mathematically identically a certain Hadamard finite part of the field on the particle, which might give you some indication of why it agrees with Pn, but in Pn, you can't use finite part at every order. At some order, you're going to switch to dimensional regularization. So it doesn't give us the full story of why these things automatically agree. It might instead be that, okay, the physical dynamics has to be the same. And this redshift is effectively the Hamiltonian, and it should have the same Hamiltonian.
Yes. Bernard Whiting and I read this argument and we basically agree, but this is valid only at low approximations, but at higher
yeah, so I'd like to talk to you about that more, because it's interesting. So for us at linear order in perturbation theory, it's an exact equivalence. And so I'd like to talk to you about what order and mass ratio in PN theory you start getting the difference and ambiguities in finite parts.
3 PN order, 3 PN.
But what order in the mass ratio?
No, arbitrary mass ratio.
For all mass ratios?
Yes.
Okay. So that's interesting. Yeah.
So I think that we shall close the session now, and thank you again, Adam, for this nice talk.
Thank you.